So here we're going to return to familiar example where we have a particle P that's rolling along this semicircular surface. This surface is frictionless and it also has a radius of r. And so we start by drawing our reference frame. So here we have A1, A2, there's O. And then because P is essentially rotating, we can draw a B frame as follows. And so if we were to draw our free body diagram for particle P, we have two forces acting on this particle. We have gravitational force, and then we have a normal force acting in this B1 direction because that is because the particle P is in contact with the surface there. And so if you look at these two forces, mg is conservative, n is non-conservative. However, if you look at the direction in which P is moving, so at this instant in time, it's moving in this direction here, which is perpendicular to the direction. If I draw out here, this is our normal force. It's perpendicular to the normal force. And so what that means is that the work done by our force, our normal force N, is 0. There's no movement of the particle in the N direction. And so while we have a non-conservative force in our system, it doesn't do work. And therefore, we can still use the equation that we just introduced, the conservation of energy, which says that the kinetic energy plus potential energy is going to be constant. Okay, so now let's go ahead and fill in each of these terms and use this relationship in order to derive equations of motion. So we'll start. Our position vector is equal to ROP, and so that is equal to RB1, and then our velocity vector is equal to the derivative of that, and using the magic formula we get 0 plus theta dot B3 crossed with RB1, so that gives us RB2. And so with that, we can plug that into the equation for kinetic energy. So remember that kinetic energy is going to equal 1/2 m, and then we have our velocity at P squared. So this becomes 1/2 m, and then V is equal to RB2. Oops, sorry. R theta dot, sorry, B2, and this is squared. And so when you're multiplying, when you're taking the square of this velocity vector, this B2 term disappears. And so what you ultimately get is 1/2 m r squared theta dot squared. And that's because when you have a velocity, or when you have a vector times a vector, you produce a scalar value. Okay, and so that's our kinetic energy. For our potential energy, now, what's key is actually understanding where our reference height is. And so that is the height at which potential energy is equal to 0. Right? And so for us, that's going to be, we're going to call that the location in the A2 direction of where O is. And so that allows us to say that our potential energy, right? So remember, potential energy is equal to mg in the y direction, so mgh, whatever variable you want to put there. And so here, this is going to equal mg, and then we have r sine of theta. And again, that's because ultimately this height, or this y variable here, is equal to this length, which is equal to r sine theta. Hence that being put here. And so now if you take the sum of these two energies, so kinetic energy plus potential energy, and I said that's going to equal 1/2 m r squared theta dot squared plus mg r sine theta. And we know that this is equal to some constant c, we'll call it. That means if we take the derivative of this, so if we're taking the derivative of a constant, that's going to be 0. Then we take the derivative of this equation here, so 1/2 m r squared theta dot squared plus mg r sine theta. Ultimately, what we're going to get is 0 equals mr squared theta dot theta double dot plus mg r theta dot cosine theta. And I'm just, because I ran out of space here, I'm going to pop this up here. We can say that we can get rid of we have m terms that we can get rid of. We have at least one r term we can get rid of. We also have a theta dot term we can get rid of. So ultimately, what we're left with is 0 is equal to r theta double dot plus g cosine theta. And this right here is our equation of motion.